Hello and welcome to the YouTube screen capture to illustrate MergeSort using the PowerPoint presentation. So first, MergeSort is a kind of sort which is considered to be more efficient than the sorts we did in the earlier classes like the selection sort, bubble sort, or even the insertion sort. So what we do in merge sorting is the key to merge sort is just to merge two sorted lists into one, uh, such that if we have two lists, then the resulting list is uh, is a sorted list of the two already sorted lists. So, for example, as we can see here, the first list is 3, 8, and 9, and the second list L2 is 1, 5, and 7, and these two are already sorted. So, a merge sort is is the sorted list. Merge sort sorts these two already sorted lists into another sorted list. So the sorted list after merge sorting will be like 1, 3, 5, 7, 8, and 9. So how it works is these two already sorted lists are taken and they are compared or analyzed one element at a time from each array. I mean each already sorted array. Like for example, here from the first list, the first element 3 is compared to the first element 1 of the second list, and the smallest one is placed in the resulting array. I mean the merge sorted array. So between these two, I mean I'm going back to the previous slide again. These two lists, one is smallest. I mean, after comparing the first two elements, one is the smaller one, so one is placed at the beginning. Then again, the first number of the first list is compared to the first number of the second list. Here it is 3 and 5, so 3 is the smaller one among the two, so 3 is placed on the merge sorted list. So similarly, each element each element in one list is compared with each element on the other list, and the smallest one is placed one at a time on the merge sorted list. So as we can see, uh, the smallest one among the remaining numbers on the two lists is given the next spot on the merge sorted list. So the end result is going to be a bigger sorted list, which is created out of already sorted two lists. So here, the merge sorted list is shown right here. So to get to that two already sorted lists, what MergeSort does is it implements the principle of divide and conquer. So what it does is if we get an unsorted list of numbers, then it starts to split it up into two parts, which we can say it divides the list, and then uh, the process is continued uh, till it reaches the leaf level. That means till it cannot be further divided, or it reaches the single element level. So that is what this slide says, that merge divides up an unsorted list until the above condition is met. The uh, above condition is that merging the two lists of one element each is same as sorting them. The first statement here says that if the list contains only one element, then it is like it is already being sorted. We don't have to sort it because it's only a single element. But if it is not, then it starts dividing the list until it reaches the single element stage, that is the leaf stage. So let's explain it further with this mathematical expression. Let's say if the list is L, whose length is K, then if K is only 1, that means if it only has one element, then it is already sorted. If not, then we create two lists, I mean two parts of the list. Uh, the first part starts from 1 to K by 2, that is the halfway mark, and the other list starts from 1 plus the halfway mark, that is the K by 2 plus 1, to the last element K. So basically what we are trying to do is we are trying to split it into two parts. And again, then we start merging the left part with the right part, considering them to be sorted. So, for example, this is the unsorted list of numbers. So, according to the divide and conquer rule, which the MergeSort implements, it first divides it into smaller parts until it reaches a single element stage. So this is the first stage where it is divided into two halves. This is the second stage where it is divided further, and here we can see only 4 and 0 is left to be separated, and right here all the elements are already separated and they are in the single element state. So now it starts the merging up part. So first the highest level, it starts from the highest level or the bottom level and compares the two numbers and sorts it accordingly. So what happens is it sorts 4 and 0 as 0 and 4. So then it again sorts the each and I mean it again compares each element with the other one at a time and sorts it in ascending order. So this process continues and it merges up one level at a time until it reaches uh, to a single list level where all the elements are sorted. So this is how MergeSort works. It actually divides an unsorted list and tries to make uh, sorted lists out of the single unsorted list. So it goes on dividing the unsorted list until it reaches a single element or the leaf stage, and from there it starts to merge them up, comparing each element to the next value, and starts sorting it. So it finally comes up to the single array, I mean single list where all the numbers are sorted. So there is there arises one question like what is the time taken by a merge sort, or uh, in a technical way, let's say what is the time analysis uh, of the merge sort algorithm. So to do the time analysis of the merge sort, uh, I'm going to open a small note that I have made. Uh, let's see. All right. this is the small note that I have made for the time runtime analysis of the MergeSort. So here, first we can see that uh, the time taken by the MergeSort, the total time taken by MergeSort is taken, I mean, considered as a function of n. Let's say the total time taken is t, so it will be a function of n, because if the number of elements increases, then the time taken to sort it and merge it back to the sorted list will automatically increase. So here, uh, let me zoom it in a little bit. So here, let Tn be the function of Tn be the function of n, which denotes the total runtime for the MergeSort, and here the n is the number of elements. So we can divide the total time Tn, I mean the total time taken to execute the MergeSort into two parts. So to do that, we are splitting the number of elements in the array into two. So n equals to n by 2 plus n by 2. So the total time taken by the MergeSort Tn is equal to Tn by 2 plus Tn by 2, which means the total time taken by the MergeSort is equal to time to sort half the elements plus time to sort the other half of the elements. So let's say if the elements be x1, x2, x3 up to xn, which needs to be sorted, and if the first condition, the best condition that we may face is the number of n is equals to 1, then we just don't need to sort it, and we can just return x. I mean, we can just uh, put the whole function, I mean the whole process of sorting it into a mathematical, I mean computer function of if-else statement. So if n equals to 1, then just return x, which is the value of the number itself. And if it's not sorted, I mean if it's not a single number, then what we need to do is merge uh, the splitted portion of the uh, elements. The first half, merge sort the first half and merge sort the second half, and again merge the two halves. So the merging will take some time, and also the merge sorting the half of the two half portions of the list will also take some time. So this is what the Tn by 2 and Tn by 2 means. So moving further, uh, we can just add these two Tn by 2 terms, which equals to 2 Tn by 2 plus Cn. This constant Cn comes out because uh, because the merging the two separated lists will also take some time, and time of n. So the time also depends on the number of elements in the smaller parts. So that's from where the constant came out from. And the 2Tn by 2 is the total time taken in solving the subproblems through recursive cells. All right. So what if we further divide the number of elements, or further split the number of elements? Let's say Tn by 2. Then here Tn equals to this much, 2Tn by 2 plus Cn. So Tn by 2 equals to 2T n by 4, because we are further splitting the number of elements n into half. So this n by 2 becomes n by 4 plus the constant uh, term also splits into half. So let's say this is our second equation. Now, substituting the value of Tn by 2 uh, from 2 into 1 from equation 2, right? The Tn by 2, the value for Tn by 2 into this equation 1, we get Tn equals 2Tn by 4 plus Cn by 2 plus Cn. So, uh, so this Tn by 2 is replaced by this whole thing right here. All right. So the Tn then becomes this much right here, which is equals to 4Tn by 4 plus Cn after opening the brackets. So after doing the simple mathematical simplification, the value for Tn we get is 4Tn by 4 plus 2Cn, because here we are just multiplying the term inside the bracket by 2 and just adding up uh, these two constant terms. So again, uh, dividing equation 2 by 2 again. All right. So equation 2 is this thing right here. So we again split the n into two halves. So Tn by 4 equals to 2Tn by 8 plus Cn by 4. So this is what we get after dividing it further. Now putting this value Tn by 4 into equation 3, alright, equation 3 here, right here, Tn by 4. Let's replace this thing by this whole expression right here. We will get Tn equals to 4, 2Tn by 8 plus Cn by 4 plus 2Cn. So after doing mathematical simplification, what we get is Tn equals to 8Tn by 8 plus Cn plus 2Cn, or Tn equals to 8Tn by 8 plus 3Cn. So let's say this is our equation 5. So, from equations 1, 3, and 5, we can generalize by looking what expressions are changing in equation 1, 3, and 5. Let's see. Uh, in equation 1, we had like Tn equals to 2T n by 2 plus Cn right here, right? So uh, in equation 3, that is after splitting it into two halves, we got like 4T n by 4 plus 2Cn, and then again after dividing it by 2 again and substituting the value onto the previous equation, we get Tn equals to 8Tn by 8 plus uh, 3Cn. So the terms which are changing are, uh, in the first equation we had 2T n by 2. This is after first split. All right, this is after first split. Uh, and in equation 3, we got like 4T n by 4, and equation 5 we got like 8T n by 8. So the term changed from 2 to 4 to 8, and we can see a pattern like 2 to the power k. All right, 2 to the power k, and let's say mm, the n by the constant term is also changing by the same factor. So it becomes n by 2 to the power k, and the constant term just increased by 1 in these three equations. So uh, it can be considered k. I mean, what power the two has. So this is the general MergeSort equation that we found out, which is equal to Tn equals to 2 to the power k t bracket n by 2 to the power k plus kCa. So this is the general MergeSort equation, which we found out after splitting uh, the time function, the assumed time function Tn of the MergeSort into smaller parts, and analyzing the pattern of change of the constants. Now, uh, moving it further, uh, to get a big O or theta notation, let n equals to 2 to the power k, or 2 to the power k equals to n. Now, to find the value of k over here, we are introducing the log factor over here. So how log works is uh, log base and result equals to exponent. What it means is the base is the number which is getting affected by the exponent. Here, uh, 2 is the number which is getting affected by the exponent k. All right, so the base is 2, and the result is what's on the other side of the equation, which is n. So log 2n will be equal to exponent. Here exponent is k. So uh, the value of k here is log 2n. So now putting n equals to 2 to the power k in equation 6, n equals to 2 to the power k in equation 6, which is our general equation right here, this one. All right, so we put n equals to 2 to the power k, which gives us Tn equals to 2 to the power k T1. The term inside the bracket becomes 1 as we put the value of n as 2 to the power k, and the constant term becomes log to n into Cn, log to n into Cn, because k equals to log to n. All right, log to n. Now, uh, log to n is equals to k. So 2 to the power log to n becomes 2 to the power k, which is equals to n. So this whole thing can be replaced by, mathematically replaced by n. So we can say that the time taken, the function of time taken Tn equals to n times c dash, which is another constant we introduced over here, which is not equal to c, but just a little bit different than c, plus log n into c into n. Now, this is the term we need to analyze the time taken uh, by the MergeSort. So to determine the final factor for the runtime of MergeSort, we can see it came down to two factors: n times c dash, which is driven by n, the number of elements, and n times log n times c, which is driven by n log n. So we are going to consider the term which one is bigger, because it will be influencing the time taken by the MergeSort more than the other one. All right, so here log n is almost as big as n. If we do some mathematical calculation, log n will be will also become a considerable value, just like n. So n times log n will definitely be greater than n. So this means uh, the dictating factor of the rate of change and determining the runtime will become the n log n. So we can call it a we can call it a big theta n log n. So this is the dictating uh, dictating factor of the rate of change and determining the runtime, which determines the runtime of the merge sort. So uh, this is how a merge sort works, and this is the time analysis of the merge sort, which depends on n log n, where n is the number of elements in the list to be sorted. So thank you very much.